Last day where we were dealing with the hierarchical model of this flankers data. So I'll have to run a little bit of code to get us back to where we were. How come you didn't open up? Go away. Try again. There we go. All right. So we ran through the first bunch here, and then I think what happened was that the model was sampling rather slowly. I'm gonna run, actually, I'm just gonna run this first little bit, reading in the data. And I'm gonna skip down to where it starts by reading in the error model. And that's gonna compile. So did anybody have any questions about the content from last class where there's the general concept of a hierarchical model after sleeping on it? Did anything pop up as confusing or that you needed clarification on? All right. Yep. In fact, we're going to talk about that today. All right, so this is going. This is one where I definitely should have compiled it before class.
Do these models take longer to sample than the other ones?
Yep, because they're more complicated. Oh, there it goes. So I can open it up and I'll pop it out into its own window and pull it over, make it big.
I run one last night and it got to 10% in about 40 minutes.
Yeah. Yep.
Is that right?
Yep. Now there are some tricks that I don't plan on showing you guys as part of the class, but if you arrange to meet with me outside of class, I can show you some tricks to speed things up. But yeah, those are sort of more advanced than what I intended on showing you guys. Yeah, I do have some models that I use in my own research where I have applied all these tricks, and it still takes like overnight to do the analysis. So it takes like 8-9 hours for it to get sort of a result. But those are rather complicated models that I'm doing. So.
Have some error they will show before.
Yeah, exactly. So if you like had an error at the outset, it would. Now there are some things where you realize, oh, that result doesn't make sense, and therefore you realize, oh, I coded things wrong, and so you have to go back. So there is an iterative part of doing statistics in the applied world. So I'm just showing you the model that we had for error rates yesterday. Again, it's that simple multivariate model that we had before, where we have some set of means, SDs, and correlations, and we're combining those to express that there's some sort of multivariate normal distribution across subjects for their intercept and effect. And then this little bit here just expresses that each subject's intercept and effect gets combined to yield either a 1 or a 0 for every single trial. So let's actually go and use that model now that it's been compiled. I showed you this new model matrix that's not super useful for this particular example. Well, actually there is something useful in this example that I just haven't shown you yet. It will certainly become useful later on today when I show you some scenarios where you have variables with more than 2 levels, and when you want to express that variables can interact in your model. So this little bit we went through yesterday just creates that model matrix that is the expected as part of the input to Stan. We wrap it all up together, and I'm going to, let's see, how fast is this? I'm just going to let it go, and we'll see. While that's going, it will let me open up the RT one. So I'll open up that one. The RT, the version of the model to do the same sort of thing with RT is going to be very similar, with the exception that way down at the bottom, when we talk about, oh, not there, we talk about how the individual trials sort of are generated. Instead of being binomial, we're saying that the individual trials have a normal distribution, and that adds this extra parameter for noise. It's like the measurement noise. We also added some extra stuff here where we, inside the stand file, we did this transformation to the Z scale. So subtracting the mean RT from each RT value, and also dividing the standard deviation of the RTs from each RT value. That allows us to do those nice standard priors for these things. But then there's a little bit at the end that basically undoes all that scaling. So before we had to do all that by hand in R. Now you can just, if you had a model that had this same sort of structure, you can just copy this same model on the internal, and it will automatically transform your data for you. Let's go back to this 60% question. Yep, just doing it. So instead of having to write that the data scale inside the data, that's what, let's see, this is the error stand. So this achieves the same thing as using the scale function in R. So it actually is more typing than doing just the scale function. But the benefit of doing that this way is that at the end, you can do this little bit, which is it is less typing than having to rescale by yourself outside of R. Yep. Yeah. So well, we've added in noise as a new parameter here. So there's no noise parameter in the error rate model, and we've expressed that the scaled version of the data is distributed as normal with noise of whatever this parameter says. So I see that my CPU meter has gone down, so presumably it's ready. Okay, so let's look at the posterior samples from the error rate model. So there's a number of different parameters. There's lots of parameters in this model that we could look at, so it's probably not a good idea to, well, actually let's try it. If I just said, show me post. Oh, it's actually called ER post, isn't it? ER post. It's going to be a big, big, long table because it actually includes its estimate for every single person's intercept and effect in this table of output. So let's actually look at each parameter family by itself. So there's a parameter in that model called means, and that's across the population, what is the mean intercept and what is the mean flanker effect. So we can take a look at that. And remember, this is a binomial model. So the numbers here are on the log odds scale. So -0 on log odds scale is 50%. And more negative values get closer to 0%, and more positive values get closer to 100%. So -2.78, that's the intercept for the model, so log odds of -2.78. If we wanted to get out what the probability that corresponds to, I always forget, is it Q-logis or P-logis? It's P-logis. That corresponds to a value of about 5%, 6%-ish. So the intercept is about 6%. It has a the credible values for that mean error rate on the log odd scale goes from -3 to -2.5-ish. So if we did P-logis of that, -3. So around 4.6 to, what did I say, 2.54? So the credible interval is about 4.6 to 7.3. So actually pretty narrow range of believable values. So we're pretty confident about sort of the value of this intercept. And the other thing we're interested in, the other entry here, is the magnitude of the difference between the two flanker conditions. So how much more likely are you to make an error in one condition or the other? So again, this is on log odds scale. So it's one log odds unit with a credible interval from about 0.8 to 1.2. Question?
Could you repeat for me, please, what was the second name?
The second one is the so we coded up the model matrix so that the first column, if we look at the model matrix, the first column is the intercept, and the second column is the effect of flanker condition. So that's where I'm getting my understanding of that this means 1 is the intercept, and this means 2 is the flanker condition. So the 1 here indicates that there is a difference between, well, the two conditions differ by about 1 log odds unit in the likelihood of making an error. You can turn that into an odds ratio if you wanted. You just exponentiate it. So that's about an odds ratio of 2. You're 2 times more likely to have an error in one condition than the other. But it's in the binomial world, people are used to looking at log odds, so it would be perfectly reasonable to report just the log odds values here. Now, in what direction? So this is saying there's a difference, but there's 2 conditions, so which condition had better performance than the other? Well, that's determined, again, by how we coded up the model matrix. So it's a little hard to see here, just with the model matrix, the numbers here. If we take a look at, I guess, let me put it in here. So if I had head, and also head of the data. So we'll see here in this column, this is in theory, this column in the model matrix is just a recoding of what's in this column in the data frame. So 1, 1, incongruent, incongruent. So clearly incongruent has been mapped to 1, and congruent has been mapped to -1. And that means that incongruent is a larger value. Like it's a positive to get to incongruent. So it's positive this to get to incongruent. So incongruent is the more error-prone value. You can actually see the same thing or make that same inference by actually visualizing the model's predictions for those 2 conditions. This is giving what we should believe about the intercept and effect. But we can actually ask the model to combine that intercept and effect one way to get the one condition and the other way to get the other condition. That the math on doing that, you have to actually get, so again, we've actually got, let's say, 4,000 samples for the intercept and 4,000 samples for the effect. You actually have to go in and do it for each sample. So you get the intercept sample, the first intercept sample and the first condition sample, you get 2 condition values. You get the second intercept sample and the second slope sample, and you get the condition values. So I've wrapped that up into a nice little function. If you're working from the code that I sent you before, it actually is not going to work. It actually should just say get condition post, not condition ER post. If I run that, it's not finding anything because I didn't load it at the very beginning, at the very top. I didn't load it at all. All right. Go back down to where this is. So I've written some code in this file that does what you need to do to figure out what the condition means are. It's actually nice and flexible in that any model you give it, it's going to get at what the condition means are. That's going to become useful for when we get to the next thing, which is more complicated designs. But I've written that in this file, and I want to just load in the functions that I've written in that file. In the same way that if you've installed a package, you can just say library in the name of that package. If you've written some code in a file, the way to load in the code from that file to make the functions that I made in that file accessible is I say source.
And does it have to be in the working directory?
Yeah. So having sourced that, I now have a function called getConditionPost, and it will, it says meme unused argument. That's another error. I did a find and replace on post in this, adding ER post to everything, but for the name of this function, it didn't need ER post, and the name of this argument, it didn't need ER post. So that's why I'm having to correct the code that I sent you. But that will run through and get out something. Let's take a look at what that thing is. What it spits out, we put into a new thing called ERR conditions. What is that? So let's just see the first little bit. It's a tibble. I'm just showing, actually, since it's a tibble, I don't need to put head. It will automatically just show me the first little bit. Okay, so it's a tibble. It has 8,000 rows and 3 columns. I see there's a flanker column, value column, and num column. So I get incongruent, a value 1, congruent, a value 1, incongruent, a value 2, congruent, a value 2. What this table is the prediction for each condition. There's only 2 conditions in this model, but we'll have more complicated later. Prediction for each condition for each sample from the model. So what I need to do is now summarize that. A nice way to summarize that is with a plot. So using dplyr syntax, we take that tibble, we pipe it to group by so that we are going to group by flanker condition. We summarize, so this is going to, for each flanker condition, compute some summary statistics from all the rows in this table that are in that flanker condition. It's going to compute the median, the lower 95th quartile or quantile, and the high 95th quantile. And it's going to pipe that into a ggplot, which is going to plot the flanker condition on the x-axis and points and bars, error bars on the y-axis. So what that actually looks like is this. So this is our model's predictions for what the 2 conditions would be like. So again, on the x-axis, you've got what flanker condition it is. And on the y-axis, log odds of error. Up is worst performance. So the incongruent condition has worse performance than the congruent condition. Now you'll notice that the actual difference between these 2 dots is, let's see, it's twice the size of the value we had in our table up above for the slope. Let's see, so we said the beta here, or the value for the difference between the conditions is about 1, but in this plot, it's about 2. That's because with the way the model matrix creates things, it's always giving you half the size of the difference, not the full size, because again, it's using -1 and 1 versus what we used to use, which was 0.5 and -0.5 and +0.5. You don't have to worry about that too much. Well, except if you were to actually express this in terms of like, hey, log odds of error. So yeah, you would have to remember to, if say you wanted to express the odds ratio, it's actually not an odds ratio of 1. It's so I told you before, to get the odds ratio, you just exponentiate, so it's an odds ratio of 2.78-ish. But if it's 2.04, that feels like a substantially different odds ratio, about 7-ish. So that's one, I mean, I might modify this suggestion down the line if I figure out how to do the model matrix such that it gives out the proper size of the difference. But for now, you'll just have to remember to multiply any differences, any parameters that, or any sort of entries in this that are supposed to reflect a difference. You'll just have to remember to multiply it by 2 if you actually want to express things as like the size of the effect is this. Yeah. So one of the reasons why we were able to do this plot of the conditions is because we were able to, this get conditions post function that I used here, it takes 4 arguments. One is the posterior samples from the model. One is the parameter that you want to talk about from the model. So we want to talk about the means. If we wanted to talk about, say, the standard deviations, we could do that as well. Usually you're only interested in the means. It's also asking for the model matrix and the data that were used to create the model matrix. So the this is why the model one of the reasons why doing the model matrix actually is useful is because it makes what I do inside this function a lot easier to get out the predictions for the means. So, that's the general results from the error rate. There's another, let's see, there's another parameter in this that's the standard deviations. Again, this is on log odds scale. And these actually aren't super interesting. You might sort of have it in a table, but you wouldn't spend much time actually reporting it in the text of at least a peer-reviewed paper. There's also a correlation parameter, as I recall. Let me... core, yeah. All right, and so can anybody remember what this so there's one correlation, it's a 2x2 table, so there's only one off diagonal correlation. Can anybody remember what this correlation is again? Yeah, yeah. So it's the correlation between, so again, there we have modeled the scenario that each person has an intercept, each person has a slope, that the intercepts are all drawn from a normal distribution, that the slopes are all drawn from a normal distribution, but that the intercept and slopes might covary across the population. And this is expressing the correlation between the intercept and slope across the population. Now, the credible interval for this is pretty solidly centered on 0. So 0 remains a highly credible value for the population correlation between these two things. So there's not much to say about the correlation.
What does that actually mean in real life?
It means that people who, so if there were, say, a positive correlation, it would mean that people with a large overall rate of error also manifested a large effect, a large flanker effect, also had a large difference between the two flanker conditions. If there were a negative correlation, it would say people who had a low error rate had a large difference between the two conditions.
So this is saying that the effect of the flankers was felt by everyone regardless of their...
Yeah, there was no relationship between a person's magnitude of their overall error rate and the magnitude of the effect that they manifested. So they're independent things. All right, so let's compile and so the RT model can get through hopefully fairly quickly.
Did you type in later? Because
Did I,
Which
sorry?
model was added later? Because
Uh,
it's not in the flankers file.
oh, around 250-ish,
249.
240. Yeah, I added a little bit. I added this bit, so my numbers are now different from yours, but it's got...
No, but we still.
Okay, yeah, I can see.
Yep, okay. So packaging the data is going to be the exact same as we had before. I noted yesterday, and it's elaborated more thoroughly in the report, that a typical thing with this type of data to observe is that the RTs, the reaction times people generate in this sort of task, are skewed, and they become more normal looking if you take a log transform of the raw RTs. So that's what I'm doing here. That means that all the units that we'll be talking about are log RT or log milliseconds and things. It's okay if you don't have an intuition for that. That's actually somewhat sort of niche. But this is a common practice when you observe one of your variables. It has sort of like a skewed distribution. You can do various transforms to see if you can normalize that distribution. There can be some good reasons why you get skew that aren't solved by a transform, but so for example, if you have something where it's count data and you're counting something and most of your cases get like 0 or 1, some of them get 2, some of them get as much as 3. In that circumstance, a log transform might cut it. You'd lose all your zeros, but we'll talk in a subsequent day about a better way of dealing with that sort of skewness in count data. So that's a scenario where you probably wouldn't want to log transform. So, but this is a scenario with RT. It's very clearly, well, I won't get into why I have justification for it, but this is a scenario where I tend to log transform. So now that that's compiled, I can just package that up and run. Again, I don't need to scale because it's going to scale internally. And this should go a bit faster, maybe. Maybe not. Oh, I have refresh equals 0 here, so I have no idea when that's going to be done. Yes, so in your own code, you probably don't want to have refresh equals 0. For the RT, just to give you a little preview, since it has this extra parameter noise, we can take a look at the noise parameter. We'll also do the same thing as before, look at the means, but then we'll be able to get the predictions for what each condition is like. You had a question? How much just general measurement noise is there in the data? Like how, so in theory, I am measuring each person many times in each condition. How noisy are people from one sort of trial to another in the same condition? Usually that's not a very interesting sort of value or parameter, but it's important to include it in the model when we have information that can inform what that value is. So yeah, there are scenarios, in fact, in this world of human reaction time and sort of really simple video games, it's known that indeed the phenomena of flankers actually does affect the amount of noise that you manifest. So that's a scenario where flankers would be affecting not only the means, making a person slower than another, but it can actually make you more variable in one condition than the other. That's a phenomenon I haven't bothered to put in this model, but it's possible to put it in the model using a simple elaboration of what we had for the model. Yeah, that's easy to do too. All right, so that actually ran through pretty quickly. So we can take a look at the posterior on the noise. Again, this is on the log milliseconds scale. You could exponentiate to get back out to what the non-log scale is, but it's suffice to say, there's some noise, but it's actually, you're pretty confident that it's around 0.16 log milliseconds.
What does that mean? Sorry.
It's not zero. It'll mean more when we take a look at the means.
Okay.
So the intercept is about 6.3, and the noise is about 1.7. So the magnitude of like how far away the intercept is from zero is much greater than the magnitude of the noise. So that gives you a sense as to like how
So
big.
you're saying you're adding the noise to the credible interval of the intercept?
No, you're just getting a separate independent credible interval for the intercept. What I'm doing is I'm just trying to give you a feel for what 0.16 means
Yeah.
by saying people on average have a value of 6.3-ish. Now, there actually is an effect of flankers of about 0.04. So the amount of noise you have is actually about 4 times bigger than the magnitude of the effect you are interested in. Say we're just interested in the difference between the two flanker conditions. This is actually showing there's actually quite a bit of noise relative to the magnitude of the flanker effect. That a given person in a given condition is expected to vary about 4 times more than the expected difference between conditions is.
So the noise is giving you like a benchmark to see if the other two are actually anything at all?
You could use it that way, like in terms of a clinical significance type thing. Like if only consider effects that are bigger than the amount of measurement noise you observe to be reasonable. That would be one way of actually letting the data determine what you call clinically significant using the noise value. That would be one thing to do. But if you're actually just interested in the basic science question of, is there an effect in the data? It wouldn't matter like the ratio of the noise to the effect at all. What would matter is simply that whether the effect, the credible values of the effect included 0 or not. In this case, the credible values for the effect again is the second entry here, and it's about 0.04. It's a small effect relative to the noise. It's also a really small effect relative to the overall intercept, but it's an effect that excludes 0. So it is an effect that's there if you wanted to do sort of a basic science theory of how the data, how the mind is working in this experiment. You'd have to include that this effect is there in your model or in your theory.
Can you explain what these 3 numbers mean? Like,
Yeah.
This was our project. What would you tell?
Yeah. Here's, let's see. Maybe I'm gonna try it not logging RT, because that way I'll be able to touch on maybe a little bit more of your intuitions. So it'll take about a minute and a half. I guess you're thinking about this because you do transform one of your variables yourself, right?
I would like to, but I don't know what it means.
Yeah. It just means that you're doing inference on the log of whatever the original scale was.
Yeah.
And
yeah, no, I mean there is that, but I think also just we get these numbers out, and then I always feel like I don't really know.
okay,
What that
yeah,
means in
yeah,
real
we'll
life.
walk through it a little bit. Yeah, with the having it as a number that people have familiarity with, i.e. seconds or milliseconds, would be better.
So to get it out of the log, you you just?
I just reran the model, not
Okay.
giving it log RT, but just the raw RT column.
But if you took the log RT answers, could you just exponentiate them out, or does that not work?
It doesn't work because that difference, you can't exponentiate that difference. You'd have to get to the condition means and then log exponentiate the condition means. So it would have taken more than 90 seconds for me to do it that way. You can actually certainly do it that way for like publication, and I've seen people do that. But for showing you guys, I just reran it on the rig. So even though it says LRT, I gave it just the raw reaction time. So all these numbers are now on the scale of time you're familiar with. So it's actually milliseconds. So 92. So there's about 92 milliseconds of noise in the data every time a person reacts. There might be, say, 500 one time, 550 another time, 430 another time. So there's noise in how, in a given condition, how much or how fast they're going to respond. Pretty tight credible interval around that value of 92, so 91 to 94-ish. So we're pretty confident that that's the amount by which people manifest random noise. Let's take a look at those means. So again, the first one is people's overall mean. So overall, people reacted within about 500 milliseconds, 553, 554-ish, with a credible interval about 539 to 568. So a little bit of variability, or I guess a little bit of more spread in what we would find credible about the population's mean reaction time.
But this first mean is regarding the condition that they are.
Yeah, regardless of the condition. Yeah, so it's the intercept of the model. It's the overall reaction time regardless of condition. The difference between conditions is this second thing. It's about 23 milliseconds. And ranging for credible values between about 21 and 26 milliseconds. So that's actually, we're still fairly confident about sort of its value. So comparing these, we had sort of 92-ish up here as the noise. So certainly noise is much bigger than the effect that we managed to see. So this is one reason why in these experiments you actually make many observations per person per condition. It's because the observations in any given condition are so noisy. So you need to take many observations in order to let the model average out that noise and find the true value sort of within the noise. The noise isn't, well, it's about 92, and the overall average is about 550. So you'd expect people to range in their RTs on a given condition, I don't know, between like 300 to 600 or to 700-ish. So does that give you a better sense as to those, what the noise means versus the actual parameters for the means? We can actually combine these just like we did with the error rate data. We can combine them to get the condition predictions, like what is the RT in each condition. I mean, conceptually, you can just look at this and say, okay, 553 plus 23 to get to one condition, 553 minus 23 to get to the other condition, and that would give you sort of point estimates for what those two condition means would be. But if we want to have the nice credible intervals on each condition, we can use this get condition post, take off this RT bit, and we already sourced it in, so I'll take this bit off. And this first argument is just named post. So that should work now, though. And we'll use the same visualization as we had before. Again, flankers on the x-axis, incongruent and congruent. And on the y-axis, it says mean log RT, but because we didn't do the log RT, it's just mean RT. In each of these conditions, it would be, this is saying in the incongruent condition, it was about 577, and in this condition, it was about 530. So it has that same issue as before, where this is a bit difference of about 67 milliseconds, whereas the value we had in our table said 23-ish. So it's because this is half of what it should be. But yeah, you just have to remember to double that if you want to say the difference between conditions. I might have a fix for that next class. So the last thing, well, no, actually, I'm going to leave you guys to look at the report, which actually does both of these models at the same time. I wouldn't expect you guys to need to choose data that needs that sort of complexity. Certainly for your report, just either analyzing the error rates or the RTs, if you had sort of a data set that looked like this, would be sufficient. If you wanted to check out what it looks like to try to actually do both variables at the same time, you can check out the report. The extra little bit that, oh, actually, one last thing. So the extra little bit that that will achieve is allowing you to look at the correlation. So if I look at this RT post-core and look at the correlation, we already had for the correlation between the intercept and the effect in error rate. And now we can look at the correlation between the intercept and effect for RT. In error rate, there wasn't a correlation. In RT, there actually does appear to be a correlation. At least the credible 0 is not a credible value for this effect or this correlation. It's positive, so those with larger overall RTs are also manifesting larger differences between the flanker conditions. So, go ahead.
Where did you see that in ER didn't have?
Okay, if we just, I'll just say ER post. This is the correlation for the ER post. And remember, we had this credible interval on the correlation that is pretty fairly solidly centered on 0. 0 is in this range. So in error rates, the intercept and effect don't correlate, whereas in reaction time they do. The extra little bit that the model that's reported in the example report I showed you achieves is that it is able to, it's going to have basically the same values as everything else I've shown you, but it's going to have an extra large correlation table because it's looking at 4 variables possibly correlating: the intercept and effect for RT, the intercept and effect for error rate, and all the possible correlations between all of them. So that is a benefit of that model if you happen to be interested in those extra correlations. Again, for your stuff, I don't expect you to have that extra level of complexity. I just wanted to give you an example of something that was fairly complex that traditional tools and methods would not be able to evaluate at all. All right, so that's it for going over the report for now. What I'm going to do is I'm gonna close RStudio. I'll save though, and I'm gonna create a new folder. I'll call it Ant, and I'll start up RStudio. So what we're going to go over now is so downloads, state modified. Well, I guess this puts them all at the bottom. So I'll set this as working directory, and I'll open up a new file. And I'll immediately save the file, and I'll call it ants.r. So I'll load in the tidyverse. You guys can go ahead and just don't bother trying to type and follow. I'll send this back out to you guys when the class is done. So I'm going to load in tidyverse. I'm also going to load an RStan, I guess. But I'm also going to load in that library called Easy that I had you guys load in the other day. I had you loaded in for just the Easy Core function that made that pretty correlation visualization. The Easy package also has a data set that I want to use, so I'll call it data ant. So I'm going to run all this. All right, so we should now have in our environment something called ant. I'm going to turn it into a tibble because I like tibbles now. As tibble ant. Okay, so what does ant look like? It's got about 6,000 rows and 10 observations. 10 columns. This is actually very similar to the flanker dataset that I just sent you. It's just a slightly more complex experiment. So it actually has a column called flank that has various values in that column. But it also, and this subnum column would be analogous to the ID column we had before. So it's identifying observations from which people. Each row, again, is a trial in the experiment. So there's, in this experiment, it's the same actually thing as we had before. People were responding to schools of fish. So you actually get also an RT column and an error column. One thing that Easy has that I haven't shown you because I've been trying to find a way to do it with dplyr and all those tools, but I haven't been enthused with what I found, so I'll show it to you now, is an easy précis function. Oh, and it's not going to work because I turned it into a tibble. All right, hold on. Let me undo this. So I'm going to remove ant. I'm going to put this before I turn it into a tibble. Okay, so I removed ant. I loaded it back in. I did the précis on it before it got converted. And so this is another way of summarizing a data frame object, another view of it. So what this is saying is that there's this meant, I guess, 10 columns. It's telling for each column is listed over here, and it's giving you a sort of a summary of what's in that column in these different columns of this summary table. So it's saying that the subnum column in ant is a factor. It has 20 different unique values, and they range from the number 1 through 20. There's another column called group. It has 2 different unique values, and one is control, the other is treatment. Block is a number. There's 6 unique values in that, ranging from 1 through 6. Trial is a number, 48 unique values, ranging from 1 through 48. Q is a column. It has 4 different levels, and this little bit shows just the first level and the last level. There's 2 other levels in there because it says there's 4, but we're not seeing them yet. Ditto flank has 3 levels, but again, we're only seeing 1 level and then the first level and the last level. So I showed you above a little bit of it. There's some congruent values in here, so we can probably guess that the middle value is congruent. I'll skip the location and direction because that's not pertinent. What is the RT column. It's saying that there's 5,760 unique values in that column. Well, because you don't expect reaction times to repeat, particularly if you're having 4 decimal precision in the recording of those. So, but the min and max indicates the range of values that sort of are observed in this data set. So ranging from about 179 to 657. In the error column, before we had a column that was logical. This time it's already being converted to a number. So there's 2 values, 0 and 1. So this is a data set where we could actually go and do the analysis as we had before, where we, if we filtered it down to just the congruent and incongruent trials, then we'd have the same data that we had before, or similar data. But now we actually have a slightly more complicated design. There's 3 levels of flanker. There's also this other variable Q that has 4 levels. And then there's this final variable group that has 2 levels. I'll say that the Q and flank conditions or variables are what are called within subject predictors. Each person experienced every level of flank, and each person also experienced every level of Q, and they actually combine orthogonally so that there's within each level of flank, each person experienced every level of Q and vice versa. The group.
An example for that, sorry.
Yeah. So another neat tool that's in the easy is the easy design function. And this kind of helps you see the different variables and which people experienced the different variables. So easy design, if I remember. Okay, it's got an X I'll put as Q. So you're mapping different, this is kind of like ggplot. It's a shortcut to ggplot. So I'm doing some aesthetic mappings. On the y-axis, I want to map subnum, rows equals flank, and columns equals group. So this is going to produce a little graphic that is showing you for each person is on the y-axis. If you see a block, a colored block, that means they have data for that condition. So the first thing to notice is that there's 2 columns here, group equals control, group equals treatment. And all the people that are above 10 have filled in data for the control thing, but not filled in data for the treatment thing. That's because everybody above 10 are the control group. Everybody in the below 10 don't have data for control, but they do have data for treatment, so they're the treatment group. So that makes it clear that group is a between subjects variable. It's manipulated. For a given person in your study, they only experience one level of that variable. Either they're in control or they're in treatment. For all the other variables, you actually have, so for this person 20, across each of the Q conditions, which are on the x-axis, they have a entry, sort of a colored block here in the flanker is neutral. They have a color block across all those in the flanker is congruent, and they have a color block for flanker equals incongruent. So they've experienced all of the combinations of Q and flanker conditions across. Yeah, that person has experienced all levels of all those variables. Does that make it a little bit more clear? So we could actually compute for a given person their queuing effects, their flanker effects. We can't compute for a given person a group effect because they're only in one group or the other. We're actually not going to talk about the group variable today because that's a slightly more complicated model than I have prepared. So we're going to just talk about the idea that you have the flanker effect and the queuing effect. The flanker effect takes on 3 levels. So that's a new thing to us so far. So far, we've only ever been dealing with 3 levels. Queuing effect takes on 4 levels. That's obviously new too. But the idea that we can also look at how the flanker effect may differ depending on what queuing condition you're in. That's called an interaction, and that's new too. So what I'm going to do is first deal with, let's just ignore the fact that there's this Q condition in the data at all. We're just going to imagine we just have this flanker condition here, and we're going to formulate a model that has 3. Before we had flanker as the only thing as a predictor, and it just had 2 levels. Now we've got flanker as the only predictor, but it actually has 3 levels. So how are we going to deal with that? First thing I'm going to do is I'm going to go get the model that we were dealing with just now from the example. Downloads, example. So I'm going to grab this RT because I'm not going to do a complicated, I'm just going to do RT. You could, even though there's an RT and an error column, you could do one or the other or both. We're just going to do RT for today. So now I've got rt.stan in here, and I don't actually need to change anything in it. The way that I've structured this to accept a model matrix as its sort of input for predictors means that I actually don't need to change this model to expand to this new scenario of 3 levels. What I do need to change is how I generate my model matrix. So I'm actually not going to do this turning it into a tibble. I'll just do it right here. Remember, we need to set the options. I said that whenever you're doing this model matrix stuff, you want to set the contrasts so that they have this contour Helmert. And if you ever happen to be curious about this and you look up what is contour Helmert, or what is this doing, the only thing that is pertinent here is this bit, the Helmert. This bit, in theory, could be left off, but this command is expecting 2 entries in this value that you're supplying to the contrast argument. So contour poly is just a default thing that we won't use at all. But the Helmert means that it's applying that center and difference contrasts. So we'll use the model matrix command. Data is ant. And what is the name of the other thing for model matrix? It's called object. Object, and is expecting a formula. So we say object equals, and then we just put the tilde. And in this data set, the ants data set, that column with the flankers condition is called flank. So it actually, we haven't changed anything even in our construction of the model matrix.
So you want the tilde there to indicate the function?
A formula.
A formula.
Yeah. So.
Where is it getting that from?
I don't even know why it needs that. I guess I might even be. No. This formula, there's actually other analysis tools in R that made formulas very popular. So that's why this model matrix command wants the thing that you're supplying as the value to the object argument to be a formula. Later on, sorry?
It's not actually a formula.
Well, later on we're going to express like flank by Q,
Okay.
and that really starts to look like a formula. It's actually flank plus Q plus flank by Q, and this is a formula expressing that you want a model with predictors consisting of the main effective flanker, the main effective Q, and the interaction between flanker and Q. We're not there yet. So we just have the simple one. So if I look at the head of that model matrix, we now have, oh, I didn't run this little bit. I know that because I know what these things are supposed to look like. So I'm going to run this yet again. There we go. So before, when we had 2 levels of flanker, we had an intercept and a flanker column. Now we've got 3 levels of flanker, so we're going to have 3 columns. An intercept column, a flank 1 column, and a flank 2 column. Now, this is a little bit it actually doesn't So it actually doesn't matter for like the math whether you do this, set these contrasts ahead of time or not. If we had forgotten to do that and we got out this other model matrix, the math would all still work out. And we can always convert between the two. I tend to prefer this one because, again, this is talking about, this allows us to, at least for this first one, to talk about something that we might actually be interested in, which is the difference between two conditions. So let me actually pull up my camera and elaborate this. All right. So if we have 3 conditions, so A, B, and C, and say A is here, and B is here, and C is here. Shoot. Okay. So the intercept, of course, is, well, before I talk about what the intercept is, it's this distance, just like we had before. And in fact, the intercept is the same as we had before. It's the halfway point between A and B. So this is the first effect, and this is the intercept. But what about this other point that's way up here? Well, that other point that's way up there is now going to be the difference between the intercept point and where this point is. So where this was like a really intuitive thing that, okay, when we only had 2 variables, we're actually interested in just the difference between these 2 things. Now we've got 3 variables. We can still have that as a parameter, call that 1. But now we'll have this extra thing 2 that doesn't actually like correspond to any comparison that we actually are interested in. But that's okay, because we can afterwards make any pairwise comparison that we want. Let me give you the alternate way of doing things.
I thought we had 4, not 3.
This is for just the flank. So the cube predictor had 4 levels. The flank predictor just has 3. Congruent, incongruent, and neutral. All right, so if we did it a different way, such that A, B, C, we could do it the way I showed you the first day, where we have one thing that is how to get to A, another thing how to get from the 0 to B, and yet another thing how to get from 0 to C. Lines don't match up there, but that would leave us still in the same position of having to then say, okay, what then, given this arrow size and this arrow size, what are the differences between these 2 things? And given this arrow size and this arrow size, what is the difference? So you'd still be in the situation where you had to compute something afterwards to make something sensible about, make sensible statements about what you should believe about the difference between conditions. At least with this version of things, you at least have one thing that already makes a sensible comparison, and you then have to only do sort of backwards comparisons just for, or backwards computations just for this other thing to say, okay, what is, given all these things, what then is the difference between these 2, and what then is the difference between these 2? So it actually, like, if you actually felt more comfortable with this way of thinking about things, just don't do this little bit here. And that will create a model matrix that has, it treats the first level as the intercept and is comparing. I showed you in this graphic that they're all comparing against 0. It actually doesn't. It actually says, okay, I'm going to call A the intercept. And now how far away from A is B and how far away from A is C are the things that it is computing or it's parameterized as. So that's why there's zeros and ones there.
Why zeros and ones?
Because it's saying everything has an intercept, or everything in both versions of the coding, there's always an intercept. Every data point, you say go up to the intercept. For the trials where it's actually that first level, which, let's see, is in this, the way this is being coded, the first level's neutral, I think. Whenever it encounters a row where it's the A, let's just use the ABC. Whenever it encounters a row where it's an A, it's going to have 1 for the intercept to get to A, and then it's going to have 0 for both of those other columns because you don't need to go anywhere else once you get to A. When it's the condition B, you have to go 1 to get to the intercept, but then this much more to get to that level, to get to the B level. And finally, if it's the C, you have to go, again, that much to get to A, but then whatever the C contrast is to get all the way up to C. So it's, when you have a variable that has multiple levels like this, regardless of how you structure the contrast, they actually, like, the table you get out is not going to make a lot of sense. What's going to make a lot more sense is those condition means. Regardless, the way you do the model is you get the model matrix and you let the model churn on the, so let's see. No, I didn't. So I'm going to say mod equals rstan model rt.stand. So we're compiling the model here. While that's compiling, I'll prepare. So actually, I'm just going to go copy the code I had for this. And that's not going to open until this is done compiling. That's annoying. Open it in another program. All right. So, just copied the code from our last example, but I know I need to change a bunch of things. So it refers to everywhere I see dat. I'm going to refer to ant. Oops. Oh, this just opened. Instead of ID, there's a subnum column. But otherwise, should be able to run all that. And I just called it mod in this example. That will run, hopefully fairly quickly. That's running. I'll copy a couple more things from again, while that's running, I'm going to copy this. So when this is done, we're still going to have a parameter called LRT noise that is just one entry. It's the amount of noise that you might expect from a person from trial to trial in a given condition. We're still going to have something called LRT means, but it's, before we had 2 entries in that, it's now going to have 3. Those first two entries are going to be, again, easy to interpret, thanks to the fact that we coded it with this sort of contrast coding. But the third one is going to be this weird, okay, is it, what is the difference between the intercept and this third point here, which isn't super interesting. But when we compute out the conditions, we can actually figure out, okay, for each condition, what is the value, and we'll get a plot with 3 points now with the credible intervals on them. And I'll give you some tips on interpreting those plots. I'm getting close to end of class, though. Pardon me? Scroll up. So this is just copied from the other, what we did the other day, where we'll take the posterior samples, get out the means, combine that with the model matrix and the data, and that will give us something that contains for each sample, in each condition, what is the prediction for that condition. And then compute some summary stats per condition across the samples and visualize. So I guess just to preview while that's going still, because one of the chains seems to have gone rather slowly. If I actually did want to include that other variable q, I can, if I wanted to include flank as a main effect and q as a main effect, that's how I would do it. If I additionally wanted to have that flank and q can interact, that is, that the size of the flanker effect might vary depending on what q condition you're in, you would do flank colon q. And now a simplified way of writing these three things is to not write this, and instead of a plus, put a times here. You'll see that some places if you are looking around with our code. This flank times q implies the full flank plus 2 plus flank colon q. Stop my phone. And in theory, this is done. Yes, no. So there is a new warning that we haven't seen before. There's divergent transitions. We might follow those rules, but don't have time to talk about them today. Come on. Oh, there we go. It was back. Okay, so mean amount of noise in this is a little bit less, 60 milliseconds, than the other experiment. Again, there's three things for the output of the means: the intercept, that first effect, but then the second effect, or the third effect, is something different. So it's important to visualize this. Oh, not dat, ant. Flank. And this needs to be flank. And something's gone wrong with the model because that's not right. But it's end of class, so I wonder. Yeah.
Mike, how many assignments are remaining?
We're actually only going to have time for the one more. So, yeah.
Is it still going to be worth 60%?
Yeah, so it'll just be prorated across all of them to be
So
60.
the grading would be for, instead of 12, would be like 8?
Yeah,
The
yeah.
same grading, and the project would remain
Still be the,
about
yeah,
40%.
yep.
And have you already checked the